Hi, everybody. Welcome and thank you for joining us at today's webinar, Accelerating Inverse Problems via Surrogate Models using JuliaSim. I'm Misha St. Amand. I'm the head of marketing for JuliaHub, and I'm joined today by today's presenter, Dr. Ranjan Anantharaman. He holds a PhD in mathematics from MIT, and at JuliaHub, he helps customers leverage modern computational methods through JuliaSim as a sales engineer. I'm excited to have him here today. I wanted to let you know if you have questions, please put them in the Q&A and we will answer them as we move along, and we'll save some time at the end to also answer your questions. One question that often gets asked, will we get a recording of this webinar? Yes, you will. In the next day or two, you will get a recording of the webinar as well as any supporting materials that Ranjan mentions, and we'll share it with all our registered attendees. Now I'll turn things over to Ranjan.
Thanks for the kind introduction, Misha. So hi, everybody. My name is Ranjan, and I'm a sales engineer at JuliaHub. My background is broadly in applied math, and I've worked with surrogate models for a while. Okay, so is my voice echoing to you guys, Misha, by any chance? I just see a little question there.
I don't hear an echo. No.
Okay. Let's.
There's a slight maybe. Just a little bit from the conference room, but nothing too crazy.
Okay. Yeah, if folks have audio trouble, let me know, and maybe I'll stand a little further from the mic and see if that helps. Okay. So hi, everyone. So today we're going to talk about accelerating inverse problems using surrogate models, and how you can do all of that using JuliaSim. So JuliaSim is JuliaHub's modeling and simulation product, which provides sort of easy workflows for lots of your standard modeling and simulation workflows, as well as a new set of workflows that we are calling scientific machine learning. So, but first, before we get into that, maybe I'll tell you a little bit about who we are. Yeah, who we are. What exactly is Julia? Why is everything prefaced with the word Julia, or prefixed with the word Julia? So Julia is a programming language. It's sort of a modern scientific programming language that is very good at, it's very fast. It's, say on the order of C++, but is also, lets you get that speed with, with very little code. So what that effectively means is that you can write Python-like scripting code, but get C++ type performance. And so if you look at this chart here, Julia is on the bottom left when it comes to execution time. So better, low execution time is better. And then compressed code size, which, so lower code size is better. And that's really sort of, Julia is trying to answer this productivity performance trade-off and trying to answer it in sort of a, in a positive way. So what does that mean in terms of modeling and simulation is that the Julia ecosystem has spawned a number of really high performance libraries. So one of the core libraries that we're talking about here are differential equation solvers. So solving ordinary differential equations, partial differential equations, dynamical systems, things like that. And it usually tends to be about an order of magnitude to 2 orders of magnitude faster than the other tools out there. And there's sort of many sort of references you could look up to sort of see, or download the software on your computer and try it out to verify most of this. So if you look at the just to give you a flavor of what I mean by this, if you look at the benchmark plots on the top right, top right, and bottom right, these are called work precision diagrams. So how much time? So these basically answer the question: if you want, a solution to a particular accuracy, how much computational time should you spend? And so, if you want more accuracy, you need to spend more time. And each of these plots here is an indication of how much time you need to spend to get that accuracy. And you'll find that the Julia tools, you need to spend the least amount of time to get the accuracy. And you'll see the green line over here is at the bottom. Similarly, the Julia tools, which over here, are at the bottom. And so that tells you, something about the speed. Now for JuliaSim, JuliaSim is what we're calling scientific machine learning for enterprise. So to to sort of tell you what I mean by scientific machine learning in the context of broader modeling and simulation, it's sort of the confluence between traditional scientific computing, modeling and simulation, and machine learning. And so with scientific computing, you get much of these standard workflows, building your models, having robust integrators and solvers, nonlinear solvers and differential equations integrators. You can build controls with your models, but the world of machine learning is somewhat tangential in some sense, or completely sort of separate, which is how do you universal approximation, how do you specify neural network terms, in many of the classic machine learning Silicon Valley contexts, how do you build image classification algorithms, vision algorithms, and so it seems to the casual user that these two are completely different worlds. Whereas over the past 5 years, there's been a huge effort to get these worlds to converge, because there's a lot of ways where traditional modeling and simulation workflows can benefit from the state-of-the-art techniques that are being developed in machine learning at a rapid pace. So this is what we call scientific machine learning. And scientific machine learning means that your simulators are differentiable. You can use automatic differentiation and back propagation and those sorts of things to differentiate through your physical models. You can do data-driven surrogate modeling, something I'm calling inverse problems, equation discovery. So can you augment models with data-driven terms and then learn those data-driven terms? Can you work with the fact that most scientific applications operate in small data regimes? This is also something that's kind of important. And so this sort of broad discipline tries to answer all these questions with these tools. Now, JuliaSim is this set of tools brought to the enterprise. In this, to sort of show you how what we've decided to do with this webinar is to take you down the path of one specific problem or one specific vertical, which is inverse problems and design problems. So maybe first I should define what an inverse problem is. And an inverse problem is basically a problem specification where you have a data set and you're trying to find the list of causal factors that arise to that data set or that lead to that data set. And specifically in the context of this webinar, we're speaking mostly about how do you infer the parameters of a dynamical system that generated that data. And so that's what I mean by an inverse problem in this particular case. So you could sort of think of them interchangeably with other terms such as parameter estimation, and so on and so forth. And to some there's sort of another adjacent, slightly different discipline called design optimization, but the methods to solve both problems are roughly similar. So let's say so both of these are optimization problems rather. So in the context of optimization, how is SciML sort of beneficial? So SciML helps you get faster convergence, and it does it one of two ways. First is getting gradients. So if you have a loss function that you're trying to regress against, first you get fast gradient calculations. How do you get these fast gradient calculations? Through the fact that your simulators are differentiable. So because you have differentiable physical models, you get you can then calculate sensitivities very quickly with an adjoint method, and fast function evaluations. Right. So these are sort of the two things you need for fast convergence. So faster gradient calculations gives you fewer iterations. Faster function evaluations, makes the iterations run faster. And under faster function evaluation, so this webinar is mostly going to be focused on point 2, which is how do you generate a surrogate model of the dynamical system, which is embedded in the loss function, and then use the surrogate model for, to accelerate the downstream optimization problem. So you see that the SciML is sort of giving you the basic tools you would need to ensure these types of designs are quick and scalable. So how does it do that? But before we get into that, maybe I'll tell you a little bit about how exactly, before you even start to tackle a specific problem, what are the sort of the landscape of tools that are at your disposal to tackle these types of problems, right? So so as I mentioned earlier, Julia is an open source language. The set of techniques for scientific machine learning has a very strong open source component. So all the differential equation solvers are all open source. But then, for enterprise, we've sort of built this 3 or 4 layer stack with a bunch of tools that are sort of handcrafted for modeling and simulation and scientific machine learning. So the first thing at the bottom is modeling toolkit.jl, which is our sort of design language. So this is how you would write JuliaSim models, so to speak. Instead of writing pure modeling toolkit code, we provide a set of libraries, sort of pre-built proprietary libraries. So if you're trying to do battery simulation or HVAC simulation, you can sort of drag and drop these pre-made libraries. And then, of course, add your own using modeling toolkit.jl. In fact, last week we also had a webinar speaking, or maybe that's 2 weeks ago. We had a webinar speaking about how exactly you would use JuliaSim to design HVAC systems. So do check that out if you get a chance. But on top of the models, we provide the methods, and and scientific machine learning is largely methods. And what are these methods? Model discovery, model calibration, building control systems, and building surrogate models. And of course, these are basically the entire these are the other sort of 4 pillars here. Building of building models and using scientific machine learning code. Specifically, we're going to mostly look at building surrogate models, which is the column on the right, and as well as model calibration, which is our inverse design toolbox. All right, so and now that I've covered the broad sort of JuliaSim and Julia landscape, are there any questions? Again, feel free to sort of put them in the chat, and at any stage. But otherwise, we'll go right in. So why do we want to use surrogate models to accelerate inverse problems? So let me sort of paint the picture with an example. So this is from one of our clients. They're called Instron. It's part of a large conglomerate called the Illinois Toolworks, or ITW. And the picture you see on the left here is that of a catapult system. So the catapult system is sort of an automotive testing system. And what Instron does is it sells these large bits of hydraulic equipment with that system you see on the left to its automotive customers. And what they do is they try and test the safety of their vehicles by generating forces that simulate a crash. So this sort of field is called crash simulation, and the way it does it is it uses its sort of this 2-piston hydraulic system to generate the forces that you might feel during the crash. And you can see a crash dummy over here. And usually automotive companies would put the sort of the front parts of the car that would actually experience the crash, and this system generates the force that would be experienced for a crash at a particular velocity. All right, why do we care about this system? So what Instron does today is it ships a digital twin of this hydraulic system with a piece of software to its automotive client. So this is called Crash Sim, and what they do is they try and get they perform something called hardware calibration, and this hardware calibration is usually sort of a very is a very slow process. The non-digital twin technique of doing this this hardware calibration is quite slow. It turns out that the digital twins that Instron ships with this crash sim is also quite slow. So the key story here is not really about the equipment, but about the digital twin. So if you have a better digital twin, the crash simulation software is faster. The automotive companies don't need to spend days and days of downtime tuning these things. So we find that the digital twin is slow. And additionally, in addition to shipping this they also use it for model-based design, right? So how do you improve this crash-based system? And that's something that they do that they use this digital twin for as well. Now that digital twin is quite slow as well. So for performing model-based design, well, one of the things you need is sort of a very detailed physical model, which is the picture on the top left. And what you want to do is perform some sort of design optimization or something like that. And with their current tools, each of these detailed simulations takes about 10 minutes. And so for the design optimization is expected to converge in 166 days, which is a few months. So this makes that type of design optimization and to produce the next generation of this product intractable. And so what did they do? They ported it to JuliaSim, and that gave them and that reduced that 166 days number to 8 hours. So that's one solution. So when you have a slow model, just port it to JuliaSim and it automatically becomes faster. How does it become faster? That is the subject of next week's webinar, which you guys should check out, on November 8th. But let's say you came to 8 hours, but you want to reduce those 8 hours to minutes or seconds, right? And why might you want to do this? Let's say you want to do you sort of do this design very interactively. You want to pull it up in a notebook or a script, and then try and then sort of gain some intuition for the parameter space in a very interactive manner. You can't quite use the full detail physical model, and so what you can use instead is a surrogate model. So just to give you a sense of the workflow here, you could start with sort of a detailed physical model and try and solve the inverse problem, and run into into performance issues, right? That's sort of the traditional sort of approach that we're seeing a lot of our customers take. Instead, you could build a surrogate model of the system and then try and solve the inverse problem with the surrogate model, and then try and return the optimal parameters. Now, I know a lot of you might be thinking, okay, well, surrogate model introduces some error. So how do you know that these parameters are optimal? You're right, they probably won't be, but but it's easy to test it out. So you can sort of take the parameters that you've learned, put them in the original model, and see if it matches your design specification. If it doesn't, then you know the surrogate model either hasn't converged or it has too much error. Which is feedback you take up to the surrogate modeling design process. But at the very least, you get a very good initial condition for iterating with the original model. And a lot of optimization techniques love a very good initial condition. So this is something that you can use to accelerate your design. Now that you've built a surrogate model of the actual system, instead of building a surrogate model of the objective, you can now reuse the surrogate model with different objectives. So you can solve a different inverse problem. So supposing a physical model is giving you data in scenario 1 and data, different kind of data in scenario 2, you can use the same surrogate model to sort of see which parameters led to both the data sets that you're inspecting. Okay. And of course, you can always, and if it doesn't work out, you can use it. It's easy to see, and you can use it as an initial condition. Okay, so how do you generate surrogate models then? So we have a software module in JuliaSim called JuliaSim Surrogates, and these are sort of largely physics-informed / data-driven surrogates. So you can there are ways to incorporate physical information into the surrogate model and then sort of use that use that to improve its accuracy. There's of course you can also train a perfectly data-driven, like a completely data-driven surrogate model if all you have access to is data and no physics. But really, what we're trying to see is what we're seeing is a couple of orders of magnitude speed up over the rest of the competition, as well as full order physical models, more or less. It's the speed up itself is not really surprising, but what is important and surprising and about the module is that it can give you very accurate surrogates. And sort of the way we do it is through this sort of proprietary architecture, which we're calling the DigitalEcho. So the DigitalEcho has a number of different levels of automation, but really, like, what you can do is specify a range of operation for your physical model, and then have the surrogate model continuously simulate your physical model. So, using the rest of the JuliaSim stack, the surrogate model will simulate your physical model, collect simulator information, and then build a surrogate model of that simulator. So you can see in this example over here that for sort of for this example over here, that we match the state space quite well. So that usually ends up being the surprising bit, the accuracy, because with most data-driven techniques, or to the extent to which you're data-driven, you will get a speed boost from using a surrogate model. So as I said, you could also use use a completely purely data-driven source. In this example, what we've done is we've loaded a data set. And this data set could be anywhere. It could be operational data, and then you can build a surrogate model of a dynamical system that gives rise to that data, and that's sort of like a very sort of simple formulation and articulation there. So anyway, there are many things you can do with surrogate models. There's all sorts of things, but today, perhaps, before I proceed any further, let's just make sure that we all understand that surrogate models are not perfect, right? These are sort of, I've just done my best to list down a couple of complaints, around, or a couple of concerns usually around surrogate models, right? And how exactly. So I would encourage everybody, if you had the time, to just put down your list of concerns of surrogate models in the Q&A or the chat, or whichever you have access to, so I can address some of them. But maybe I'll just go through the three major ones that I see from customers, and we can go through the ones from the chat. So okay, so the first question is, okay, well, I want to use some surrogate models, but training this thing is just like really, really difficult. Like, it's very non-trivial for me to take a surrogate model, and sort of just build a training group for a surrogate model with the tools that I'm using today. And you're right, but what we're trying to do at JuliaSim is to provide workflows for you to make that as easy as possible. And so these sorts of things can be very, very problem specific, of course, but based on our interactions with all of our customers, we try and provide workflows such as the one that we're highlighting in this webinar, to be able to use surrogate models. And like the key part of the surrogate models is usually, what are you going to use the surrogate model for? And sometimes you need to sort of train it with a little bit of knowledge of what you might want to use it for. It's and you trade that off with its reusability. So if you're using a surrogate model for a downstream engineering optimization type application, then that's something to keep in mind when training the surrogate model. And of course, you don't need to keep that in mind. The software keeps that in mind while sort of while generating the surrogate model for you. Okay. So how accurate can the surrogate model be? Which is another common concern. So these data-driven or machine learning-based surrogate models always need to be tested and validated. So we have a sort of robust set of of tools that or sort of tools that help you test and validate your surrogate models. So JuliaSim understands all of these difficulties and has like little pieces to make sure that all of these things become easy. The other thing we do is we offer surrogate models with guaranteed accuracy. Now, what do I mean by that? That's a pretty big statement. So usually, the easy thing about surrogate models is that you can learn the more training data you feed into the surrogate model, the more the more accuracy you're going to get. And usually, if you're building a surrogate model of a simulator, you have infinite access to data because it's a simulator, which is the ground truth. So now, what we try and do in our surrogate modeling package is that we try and understand that there's a certain amount of error, and we try and resample from the space to make sure to add more simulations to the surrogate model, and then really like you can go. This is sort of like an iterative loop, and so you can go until you get the accuracy that you need from your surrogate model on your test data. And this is sort of the kind of workflow we're trying to see. So if accuracy is your holdup, we have a workflow for you to be able to generate a surrogate of a model with a required accuracy. Okay. And the last one is how much does it cost to train the surrogate model? Usually people don't have access, or they don't want to sort of burden the compute clusters, like generating data like 24/7. So there are two sort of aspects to this. The one aspect is being able to the one aspect is being able to try and generate, is the time aspect, right? Like how much time does it take to generate all this data? So in theory, all of that training time can be amortized by just splitting the simulation up in parallel. So you can spawn a cloud job, and this is exactly what we're going to do in the demo. Spawn a cloud job that does 500,000, 10,000 simulations happening in parallel on this cloud compute cluster, and then all of the data is then collated back to you, which is then run for training. So, and all of this is asynchronous, right? This is shut it, forget it, use it, do something else while this is going on. And of course, we provide this on, we provide a cloud platform where you can actually do this. So we make that easy for you as well. The other thing is why even if it does, and this cloud platform tells you exactly how much time and cost it takes to train the surrogate, or to do a certain compute job. But if you're reusing the surrogate for various other design optimization tasks, then the cost that you've required for surrogate is further amortized. So time is amortized by doing everything in parallel, and your cost is amortized a little bit by reusing the surrogate as much as you want. Okay, so I see a bunch of questions. So let me just address them. So I have one question on neural networks tend to require a ton of training data. How is this overcome? So yes, neural networks do require a ton of training data. Oh, there's also another one about Gaussian models. So Gaussian models, but they suffer in terms of number of variables. Yeah, so many other techniques suffer from what we call a curse of dimensionality, and neural networks are a way to overcome the curse of dimensionality, and our surrogate models certainly do overcome the curse of dimensionality, and we have examples for that. But like yes, you do require a ton of training data, but usually in when you're doing a surrogate model for a design task, which is what we're doing now, you're making a surrogate model of a simulator, and simulators tend to have, is a source of ground truth, and so you can get, in theory, unlimited training data from it given unlimited time. And so it's quite straightforward to just, to have enough data for that. And of course, if it's not, if your simulator itself is not accurate, then perhaps it needs to be calibrated to be accurate and then generate the infinite training data. So yes, I mean, in most cases that overcomes the data problem. So okay, that's one. Let's say, can we use it? Okay, so then I have another question. Can you build a surrogate model, say a fluid dynamics simulator, and then use it in the inverse design and shape of wing? Yes, we can. So if you we definitely can. So please, if you have a specific application in mind, such as that, or you have any other, any other specific application in mind, do get in touch with us, and I'll, at sales@juliahub.com, and we'll and we can speak together on how exactly we can build a solution for you. So yes, this is and just to say once again, this is exactly the kind of thing we want to do, right? We have a simulator. You have an inverse design problem, such as the shape of a wing, and this is the kind of thing that we want to address using our tool chain and our techniques. So broadly speaking, yes is the answer. So what else? What if we don't have a partial differential equation, but you have a black box problem? Okay, let's do let's go back one slide. Sorry. Okay, so this particular slide is using a black box source. So this is a completely black box problem, and this is called a functional markup unit. It's a kind of binary that many simulators in the industry generate, and this is one of our one of our inputs into our JuliaSim framework, or JuliaSim Surrogates framework. You can just take these black box models, and then you can simulate them a bunch of times and get dynamics, and you'll have a surrogate that matches that dynamics. So yes, absolutely, you can use black box models. Of course, when it's a black box model and you don't have much insight to the physics, is a different set of trade-offs. But yes, the software does allow you to do that. All right. Last, are you using Bayesian optimization in your surrogate-based framework? The answer is no. This is an echo state. Surrogate-based optimization framework. Oh, okay, no. This is not. So the optimization, we don't. Well, this particular example does not use Bayesian optimization for in the surrogate-based optimization, but we have examples for that, or we have the module that we're feeding the surrogate model into has Bayesian optimization. So let's put it that way. And but this particular example does not demonstrate that. It's a different technique. But yeah. Anywho, please keep them coming. I mean, these are great questions. So okay. So we covered this, around concerns around surrogate modeling. And one of the things we do, JuliaSim you can use JuliaSim a number of ways. One of the ways you can do it is on our cloud-based platform, and our surrogate modeling tool is currently largely just based on a cloud-based platform, because which we call JuliaHub, and which incidentally is the name of the company. So excuse me. So you can train multiple simulations in parallel. And this ends up working quite well. And all of this data is collated, and then you can use the surrogate. And all of this we make quite seamless. So this is something that we'll demo just now. But just to give you a sense of what this kind of framework and technique can do, is that for a really large building simulation, some sort of a thermohydraulic building simulation, you are able to then you're able to generate a surrogate model which is up to 80x faster. And the key is not the 80x faster, but mostly about how accurate it is. And it might be a little hard to see, but if you look at the y-axis on the relative error, you'll see that it's well below 0.1%. And that's not to say that you'll always get 0.1% accuracy. It's just if you train the surrogate model a certain amount of time, you will converge to that accuracy. Is the larger point I want you all to walk away with. Okay. And I said earlier, like, we have an entire cloud platform to help you with the surrogate models. But we're, once the little box over here is how do you run the apps. And once all of the training data is collated, it's used, it's sort of stored in S3 and in what we call data sets. And of course, you have access to a bunch of developer tools as well. But we won't go too much into that now. Let's go straight into demo. So what I'm showing you is running on our platform. And this is the notebook functionality on our platform. It's called, these are called Pluto notebooks. And these, these Pluto notebooks, in my opinion, are beautiful. And really sort of one nice thing about notebooks is that you can sort of render the equations really nicely, which makes me happy. But anyway, so let's build a surrogate model of this nonlinear chemical reaction system called the brusselator. And I'm showing you a little bit of the equations to show you how it's nonlinear. I mean, of course, there are two sort of standard second order operators here, but like there's but they're sort of multiplied. They have a nonlinear forcing. They have a nonlinear forcing, and they're quite nonlinear. And this brusselator chemical reaction system is sort of what is called an autocatalytic chemical reaction system. It's used a lot. Happens to be used in the life sciences quite a bit as a model equation. However, this sort of equation has periodic boundary conditions, and we're going to see some of that periodicity. But what we're going to try and do is, this doesn't really matter for the perspective of this example. What we're going to try and do is take, sort of JuliaSim's DigitalEcho and then try and generate a surrogate model. The inputs to the surrogate model are these 4 parameters, and what we're trying to do is get some sub set of the PDE domain and use that as our outputs. And so this is really the problem formulation for the surrogate model. So how do we how do we do that? So let's dive right in. So the first step is to load all of our packages. So you load all the JuliaSim packages, load a bunch of solvers, load modeling toolkit, and our optimization routines, because we're modeling, we're optimizing, and we're building surrogates. And now the next key step here, which is where we're grabbing an authentication token. So this authentication token lets us authenticate with the platform and lets us spawn these cloud jobs. So all of that complexity is encapsulated in just this token here. So and the next thing we do is we sort of load the model, because the model is not as important here. I just wrap that up here. But the model code is loaded. But for the surrogate models, what we now try and do is specify a parameter range. So we have 4 inputs here. What are the ranges of parameters that we'll use that we'll use for the surrogate modeling problem? So through, in what space do I want this model to work? So we've sort of chosen a range here, which is roughly on the order of like maybe 50% or so. Yeah, so 50%, yeah, exactly. So 1 plus or minus 50% is 0.5, 1.5. Okay, and for this problem, we've chosen to simulate 500 samples, and then we capture this all of this in a parameter space object. But now that we have all of this information, the model as well as a range of parameters over which we want to sample the model, we can then spawn what we call a data generation job, which just needs a name. It needs some specification. So what is how many CPUs do we want? How much memory do we want? And what's the time limit on how long we want to run this job and not sort of bust our cloud bill, so to speak. And once we do that, we can just hit launch. And I'm not running this code now because I don't want to run an 8-hour simulation now. But this, which is why I've commented out. But like you can see, it just hits launch. And once it's launched, this is saved as a data set. A JuliaHub data set, which is stored on S3. It's our standard sort of way of interfacing with data. And you can collect all of this data into a format that the surrogate modeling tool understands. So we call this experiment data, and it's specified by ED. So once once the data generations job is spawned and it saved the data set, we can then download it, grab the ED, the experiment data object, which encapsulates all of our simulated data. And then to make sure that the simulator actually worked properly, we can visualize it. And you can see here that you can see the sort of periodic boundary condition, the oscillation rather in the system over here. And then once you capture the simulation model, you can then train the surrogate model, which is just literally just calling this one construct, DigitalEcho on this ED. And once we do that, this is now spawns off a training job, which does all of the training, and then comes back and gives you a surrogate model. So once we've written the job down, we can then spawn the training job, get the training job, and then we can go off, have our coffee, do our work, and then, by the way, and when all of these jobs get spawned, you can just go to sort of a live dashboard here, and you'll find that these jobs are all sort of are spawned on the platform here, and then there's a little tick sign when it's completed. So it's completely asynchronous, and and you can even get a notification when it's done. So anywho, now we've spawned off our training job. The surrogate model is saved as a data set as well, because that's the result of the training job. And now we can download this surrogate model, which is what I'm doing over here. So the surrogate model is downloaded, and just inspecting the surrogate model, you'll find that you see it's a continuous time surrogate model, which is of the type DigitalEcho, and then you'll see some hyperparameters and sort of neural network sizes and things like that in here. This is not really a neural network surrogate. There are some neural networks in here, but the core of this is the dynamical system, which is sort of why why it's easy to incorporate physical information and things like that into this. Anywho, now once we've downloaded the surrogate model, we can start inspecting the results. So if you look at the legend here, GT, which is the orange line, is our ground truth. So that's the reference information of the simulator, and blue is prediction. And we find that the prediction and the simulator overlap pretty much, which is good. And so that's how we know that a surrogate model actually worked. All right. Now that we've generated the surrogate model, what we want to do is parameter estimation and using the surrogate model. And to do this, I need to tell you about two things. So firstly, what is the parameter estimation software? And B, and it's a summary of its capabilities, but broadly, how do we then compare sort of using this parameter estimation software with the full order model and the surrogate model. So the comparison I've done is I've run the calibration for a wall clock time of 10 seconds, and because that's what I can do live, and sort of the full physical model for 10 seconds, and then compare the results, right? So before I show you the results, the side-by-side comparison, maybe I should tell you a little bit about what we're actually calling. So we're using JuliaSim's module for solving inverse problems is called ModelOptimizer, I mean, as you can see, sort of like how do you, given several data sets, how do you then, or data sets or objective functions, how do you then find the set of parameters that I either give you the data sets or minimize the objective function? That's sort of the two things that ModelOptimizer does. And it provides just these, there are two functionalities or main blocks of capability or branches of capability that provides. It's a calibration capability, so what I mean by that is a suite of optimization algorithms, a suite of calibration algorithms, which you can think of as loss functions, and which you can sort of compose with each other. So loss function with an optimization algorithm, and then sort of this Bayesian optimization, uncertainty quantification, which is sort of the other main pillar that it provides. The other thing that it does provide is model discovery. So can I augment my physical term with data-driven terms? So best of both worlds maybe, and try and infer the parameters of the data-driven term, and try and and now once you have the data-driven term, you can then reinterpret that data-driven term, for a basis of physical terms. So this might be a mouthful, the model discovery and the calibration. So which is why I'll refer you to another webinar that goes into it and just sort of goes into all of the detail and all of the algorithms that are provided in ModelOptimizer, and what that means for your modeling and design work, and simulation workflow. Right. So going back here, so going back here, now that you have a rough idea of what ModelOptimizer is, let's perhaps start doing this comparison. So with the ED, I've just like grabbed some metadata so that I can run a forward simulation using the surrogate. And so what I've done in ModelOptimizer is I have a DigitalEcho front end, which is sort of the interface. So which is sort of the interface between the surrogate modeling and the calibration algorithms. And so once I've run the calibration algorithms for 10 seconds with the surrogate model, I find that the surrogate model has nearly sort of converged. It's doing reasonably well for a wall clock time of 10 seconds. And you can see the orange line or the red line and the blue lines nearly overlap. But if I take my full physical model, you'll find that it's barely begun, right? And it needs a ton more iterations to start to start solving this inverse problem. Excuse me. Now to sort of because this is a little hard to see, we put together a little animation. As you can see on the picture on the left is not a static image. It's the image of the original model trying to do the calibration process, and that takes a little while. Whereas if you see with the surrogate model, you sort of it's pretty much it's really quick. It does get because the surrogate model introduces some error, it gets stuck at a local minima and then eventually comes out, and then so basically running a surrogate model for enough number of iterations, whatever that means, could give you a very good initial guess or a set of near optimal parameters for your inverse problem design or your design problem. All right, so that's a huge portion of what I wanted to show you today. I do want to share a few other examples of this that we've done outside of the sort of simple example problem. We've been able to take models of room air conditioner models within buildings and then try and build surrogate models of those. Those are sort of very detailed, multi-physics, thermodynamic simulation. So and using these surrogate models. By the way, the ground truth model for this was an FMU. So again, black box. And we were able to get convergence 2 orders of magnitude faster. So basically, we arrived at the optima before, and if you look at the picture here, you'll see that we arrived at the optima way before the first simulation would even complete from the original model. And these sort of savings compound more. The more expensive your simulation is, or the more detailed your PDE model is. Anyway, so just to sort of recap with you guys, and again, feel free recap. We have today we spoke about JuliaSim and sort of calibrating inverse problems or solving inverse problems using using surrogate models. But JuliaSim as such offers so much more, right? So you can do model, you can do this model discovery, you can build control systems, You know, and of course you can design domain-specific products very quickly using our model libraries. So I do encourage you to go to try out JuliaSim. We have you can either contact us on our sales email. If you go to JuliaHub.com, you'll be able to find JuliaSim and a button to preview JuliaSim, where you can directly get in touch with us, and you could try and either evaluate the software or depending on the kind of engagement you'd like to be involved with us. And so yeah, I would encourage you all to come check us out. And with that, I perhaps will conclude for now and see if you guys there are any other, and open the floor to questions maybe. I don't see any questions, so I think we must have gone through most of them. You know, in the surrogate modeling section.
Yeah, I don't see any other additional questions, so I think we're just a thank you. So I think we're good to wrap up.
Perfect. Oh, there's also sorry, I just saw one more question. Do we have any physics informed machine learning application? Physics informed. So all of our surrogate modeling techniques are in a sense, all the examples I showed you now are physics informed in some sense. I think perhaps what we can do is, I guess it depends on what you mean by physics informed. It's also, lots of folks call lots of techniques physics informed. So all of these are in some sense tries and incorporates simulator information as well as it can, and we have an entire sort of stack of techniques that tries to, instead of starting from a data-driven the PD in the law. Sorry, instead of starting with data-driven terms, we can start with instead of starting on the data-driven side, we can start with physical model and augment data-driven terms. That's something we do offer. But I see a clarification. I mean, including the PDE in the loss function. Yeah, absolutely. So all of these. So this example that I showed you right now includes the PDE and the loss function. So it's so absolutely. So does it include the PDE in the loss function? This one includes data coming from the PDE in the loss function. But tries to so the loss function effectively is in this example is basically data coming from the PDE minus the L2 norm between the data coming from the PDE and the PDE itself. So which parameters of the PDE fit the data that's coming? That's sort of the convergence that you saw. Instead of having the PDE in the loss function, we're just we replace that PDE with the surrogate model of that PDE. And so, which is why we saw that the function evaluations of that loss function are much faster. And that's basically what we did there. So yeah, if that's what you mean by physics informed, definitely that's exactly what we did. And yeah, the other thing is, now that we have the PDE with this system, you can use it for other things. Like you don't need to use it just for this calibration, data-driven data calibration thing. You can use it for design optimization. Like you can infer other parameters of the PDE for different use cases. And if that sounds interesting to you, please do get in touch with us. This is something we would absolutely love to talk about. And of course, the extent to which you want to provide more simulator information into a problem and talk about things like that, we would love to engage.
Okay, I'm not seeing any more questions, and we're close to out of time, so I'm going to wrap things up. Thank you, everybody, for joining us today. Thank you, Ranjan. I appreciate it, and look forward to seeing you at another upcoming JuliaHub webinar. Thanks, everybody.
Thank you.